This was my master's thesis on score-informed source separation of choral music. I did it, my supervisor was Professor Philippe Depal at McGill University in Montreal. And it was then also published in ISMIR 2020. You can see all the details in the ISMIR website, the poster, etc., and some audio demos on my website. Okay, so let me begin by just saying what is the task. So we're all on the same page. We have a choir, and we want to separate it into individual tracks for each of the choir sections. So we're not trying to separate each singer, of course. You can see even the image here was a bit hard to separate into sections. So you can imagine that a choir is very difficult to separate in audio terms. In terms of motivation, first of all, I had a personal interest because I'm a choir singer and choir conductor, and it was close to my heart. Another thing is that not a lot of people have worked on this in the past, although there was lately some work in the Trumpa project, and also there was another paper at ISMIR doing choir source separation. So it's nice to see that people are approaching this more and more. If we are able to do choir source separation, this lets us do fine-grained editing, mixing, or remixing, so to speak, and analysis. And something that is practical use is automatically to create choir practice tracks. Usually, you can find a lot of websites selling these practice tracks. Choir singers need many times cannot read score perfectly, and they can use audio tracks to help their learning. Many times the conductors record for each section their own practice track. So I think it can be nice to automatically create those practice tracks from professional recordings. Okay, on to the challenges. Why is choral music harder maybe than other genres of music, other types of music? So each source or section is actually multiple sources because each section is composed of multiple singers, and every singer has their own pitch, own timbre, and own slight timing variations. Then another problem is that as choir singers, we are often told that we should blend our voices together. And of course, the separation must undo that blend. And of course, the eternal problem of lack of data sets. Choirs are very seldom recorded as one section per track setting because choirs like singing together. This means we don't have a lot of data sets as opposed to, let's say, pop music, which is often recorded in separate tracks. Okay, I have here one example. To be honest, I don't really need to show you this example, but I just like the way it sounds. Let me know if you cannot hear the audio. Jesus Christus Could you hear that?
Yes, and it's lovely.
I know, right? That's the reason why I was showing it. So this is an excerpt from Grieg. I was looking for an excerpt where the same melody is sung solo and then imitated by the choir. Of course, the choir is singing a harmonization of the same melody, but it's interesting to look at the spectrogram and see how crisp and clear it looks when it's solo and how mushy and blurry it looks when it's choir. And this can illustrate a little bit why is it difficult to separate the choir. I don't need to go into details about, there here we can see the very clear pitch curve with vibrato, and here in the choir section, everything is just one big mess because that's what makes the choir sound so beautiful. So I approached this in two methods. The first method is sort of a baseline, an unsupervised method, and the second one is supervised learning, deep learning, using a synthesized dataset, since I didn't have access to a large dataset for training. So this first unsupervised method is score-informed NMF. NMF is non-negative matrix factorization, and it's one of the oldest techniques for source separation. In NMF, we factorize the mixture spectrogram by representing it as a product of two matrices, basis signals and time-based activations of those basis signals. Sometimes the basis signals can be called components or templates, spectral templates, but it's all the same thing. After we factorize the spectrogram, we calculate, based on the factorization, a ratio mask that we then apply to the mixture spectrogram to extract each source using the original phase. And in this case, I used an initialization scheme for the basis signals and activation matrices to constrain the factorization using timing and pitch information from the musical score. This was originally used for piano notes. It was a technique by Sebastian Evert and Meinhard Müller in 2014. So in terms of cutting edge technology, this is very old, but surprisingly, it still works. So just to illustrate, here is just an example of a mixture spectrogram, a very artificial mixture spectrogram in the center. And then on the left, it's the basis signals and the activations. And you can see how the product of these two matrices gives us the spectrogram. In terms of how do we constrain this on the score, we basically create a initialization of each basis signal using a sort of a harmonic comb based on which notes we have in the score. So one component for each note. And we initialize the activations based on the timing information when each note is being sung in the score. This is the figure on the right. I have implemented this in Python. If anybody can ever use this, please feel free. Now let's see an example for actual choir spectrogram. This is a choir spectrogram in the mixture. And then the factorization creates an approximate of the mixture, an approximation, which is the product of the basis signals, one basis signal for each note. You can see that after a factorization process, the amplitudes of each frequency bin has been modified based on the content of the mixture. And the activations also have time varying values, amplitudes, based on the intensity of that component at any given time. So how does this work for choir? Of course, I'll remind that this technique was for piano originally. So for choir, this did not capture the continuous evolution of pitch and timbre. So the voice has time varying changes in pitch and timbre, and NMF is discrete in nature. It cannot really capture these things because every note is just represented as a single spectral template. And of course, we could use several spectral templates for each note, but then how many do we use and how do we represent the continuous evolution? This is still a problem. NMF does have some extensions which can definitely improve these things, like source filter models, et cetera, and I did not try that. And okay, so this discreteness of NMF caused an undesirable amplitude fluctuation artifacts in the results. I'll let you hear it later. And this brings me to the second method, which is deep learning using a synthesized dataset. And what I did was take WaveUNet, which most of you might know, which is a source separation by Daniel Stoller. And I conditioned it on the musical score. Well, just a primer on WaveUNet. It is an encoder-decoder architecture, which takes the mixture audio, the raw audio, no spectrograms involved, and it downsamples it gradually using a series of convolutional layers until it reaches the bottleneck, which is sort of a high-level representation of the signal. And then it upsamples it using, again, a series of convolutional layers. Also using skip connections from each downsampling layer to the corresponding upsampling layer. This kind of lets it use the original signal content at each level of processing. And this worked quite well for vocals and accompaniment separation. It was included in the signal separation evaluation campaign of 2018 and got nice results. And it was also open source, so it was easy for me to build upon it. Now, if you just, okay, so let me get to the choir data set. Since we couldn't really use a real choir data set, we had to create our own synthesized data set. Of course, we used the ubiquitous Bach chorals data set because it is very regular in a sense and very predictable, doesn't have too many sources of variation. And since we didn't really have a baseline for comparison, this kind of basic data set was really a good starting point. So we have about 350 chorales. After we synthesize them, we get around 4 hours of music. The synthesis we use is just a sample-based synthesis. If you open the chorale score in Muse Score, it's a notation program, and press play, that's what you hear. It uses a behind-the-scenes synthesizer called Fluid Synth, which is just basically a sample synthesizer. It takes a set of samples and loops a predefined portion of the sample if you need it longer. And if you need a pitch that is not recorded, then it pitch shifts the samples. It only synthesizes ah, so it's kind of choir ah as a preset. And there are no lyrics, unfortunately. Now, we wanted the chorales to be a little bit more similar to the various genres of choir music. So we added some data augmentation, which is simulated breaths, where all the voices are breathing, sort of, so to speak, at the same time. There's no actual breathing sound, it's just a pause. And then we randomly omitted some notes, and we added tempo variations. There are still many data augmentations that we did not do, by the way, which is, for example, dynamics or timbre or lyrics. And this is, I think, very important in order to improve results. Just to give you an example, the original chorale looks like this. Jesu meine Seelen wohne. And then if we augment it, we remove some notes, etc., etc. We add a tempo. And when we synthesized it, etc. I won't torture you with that anymore. So this is how the dataset sounded like. Now, we trained WaveUnit on this dataset, vanilla WaveUnit, just normal, no conditioning, nothing. And it kind of worked. You can imagine that this dataset is easier than the original dataset WaveUnit was trained on, which was separating vocals from accompaniment in pop music, has very varied. Here we have a very regular dataset. One thing WaveUnit completely failed on is sections when several voices are not singing or voice crossings. So basically, the model learned to rely on the standard ordering of the voices, because that was basically the only way it could know which note belongs to which voice. However, there are situations in choir music where you cannot really know which note belongs to which voice. If, for example, you hear women sing, how do you know if that is alto or soprano, if it is in the overlapping range? There are many overlaps in the range between bass, tenor, or between tenor and alto. Even tenor and soprano can sing the same note. This is the reason why we decided to condition the model on the musical score. We have to decide how to represent the score and how to feed it into the model. These were a lot of things. We tried several things. We decided to represent the single part score, let's say the soprano score, as a time series, which indicates what pitch is active at any time. And we thought it might be helpful to align the score with the audio. So we basically use the same sampling rate for the score representation. Doesn't really have a sampling rate, but it's a time resolution. And we tried 4 different score representations and 3 different conditioning locations for the model. I'll warn you in advance that there are many other things to try that we didn't try. So which score representations did we try? One is just the basic piano roll, which is just one hot matrix, where it is 1 when a note is active and 0 when no note is active. Then we tried to just take piano roll it's nice and simple, but it is very large representation, especially since we have only one pitch active at the same time in choir. A choir section normally sings one note. And if the choir section has divisi and sings several notes, then we can just represent it as 2 choir sections, basically. So we, instead of using a piano roll, which is great for polyphonic music, we represent each part score as the second representation is the normalized pitch. Just take the active pitch, normalize it to some range, and use a special value to indicate silence. This worked quite well, but we wanted to try and also separate the pitch and the amplitude. So this is the third representation, which has 2 channels. One is just the pitch normalized to the full range, -1 to 1. And the other is just a mock amplitude channel, not a real amplitude, smooth amplitude. It's just 1 if a note is active or 0 otherwise. And then another one, which is quite novel, is to represent the score in an audio-like form. Since the network is good at processing audio, why not represent the score as a sort of sinusoidal pure tone signal, which is simply a piecewise sine function. And this actually turned out quite well, the last one, because it is smoother than the other ones. In terms of where to feed the score information into the model, we tried several options. One thing is to feed it just using in the input alongside the audio. Another option is to feed it at the bottleneck, but that is a problem since it must be downsampled and then you lose all the fine timing information that you had. And another option is to feed it at the output. In that case, you have to crop it because the output is cropped in WaveUNet. We tried combinations of input and output, and we did not try bottleneck condition. I will add also that we did not try conditioning at any of the intermediate downsampling or upsampling layers, and I definitely think that is worth trying. There is a work called Conditioned UNet from Gabriel Meseguer Brocal in Izmir 2019, and he showed there various ways to condition UNet. It can definitely be used on WaveUNet or other similar encoder-decoder architectures. Okay, so another thing is the model configurations. The basic model configurations proposed by WaveUNet is simply to have one model which takes in the mixture. In our case, it also takes the score, and it outputs each source. It uses a single model to separate all of the sources. Now, we found that if we train a separate model for each of the sources, this improves significantly the results. This makes a very big difference. And it makes sense, of course, right? Because we use 4 times the amount of parameters because we use a single model for each source. And each of those models can sort of become an expert in separating only the tenor, only the bass, etc. Now, we also wanted to somehow separate the best of, combine the best of both worlds from these 2 configurations. So we created a multi-source model, which basically receives the mixture and the score of the source you want to separate or extract. And that model can extract that desired source based only on the score. It doesn't know if it's separating alto, tenor, or bass. It just knows that it separates these and these notes. So actually you can separate an excerpt containing notes from both tenor and bass if you wish. You can even try and separate notes that don't exist in the mixture and see what happens. Okay, so we combine all of these options into 6 experiments, NMF, and then wave unit with all of the combinations of what I just said, basically. Results. I'm going to go over this quite quickly. First of all, wave unit outperformed the NMF baseline by a large margin. All of the evaluations here are using the SDR. SDR is the standard metric for source separation, source to distortion ratio. And like I said, using a separate model for each source improves significantly the results. And you can also see, which is not super surprising, that soprano is easiest to separate and inner voices are more difficult. This is consistent with what I would subjectively say is more difficult. As a person, it's also easiest to separate the soprano. Its range is very distinctive and it has less overlap in terms of range, etc. It doesn't have any voice crossings, or has very little voice crossings, let's say. Now, comparing with score to without score, we can see that the score improves the median performance for all voices, especially for the inner voices. So also I checked those cases of voice crossing specifically, and it is clear from those cases specifically that the score was, 100% effective in disambiguating those cases. And what is nice to see that the multi-source model performs pretty well compared even to the single source model, even though it uses only a quarter of the parameters. It can separate any of the sources. Comparing the score conditioning methods we tried, it doesn't make a huge difference where do you condition and how. The only worst option was to condition only at the output, which kind of makes sense because the output is just basically convolutional layer with kernel size of 1, which means it's just a dot product on a sample by sample basis. I think in terms of future work, it is very important to try a more versatile conditioning methods, to use a separate network that will predict the conditioning from the score or something like that. When we listen to the examples in terms of subjective qualitative evaluation, it does seem that the pure tone representation gives some advantage because, like I said, that's my hypothesis. Because it's a smooth representation, it leads to less artifacts at the note boundaries. But this should be probably better solved by a score conditioning network. Now, the really important part is what happens if we take this network, which was trained only on synthetic data, and we try to apply it to our real choir recording. So here we use the recordings from the choral singing dataset, which is Elena's dataset. So thank you, Elena, for providing that. We can see that actually on real world recordings, surprisingly maybe, the NMF performs better in terms of median performance compared to all the wave unit variants that we tried. And this is interesting. And what it means is that we need better data sets. We need better data augmentation methods. And maybe we need other things that I don't know what they are. But NMF has a very strict, let's say, bias towards the score. It simply uses the score to predict sort of a filter on the spectrogram. And this worked pretty well for the, or not so well, but better than wave unit, which was not trained on any examples that were similar to the real world recordings. So that is the bottom line. I don't need to repeat it. Next steps, I already mentioned some of those, but yeah, it's very important to work on multi-track data sets. I think that is can be super useful to collaborate with learning track websites. Any of those websites that I was mentioning in the beginning, they have huge data sets. They just don't want to give it for free, but maybe they could for science, who knows. One thing that could be useful is that now there are so many virtual choir initiatives like Stay at Home Choir, which is a London-based one with thousands of singers. Imagine one of those choirs just donating their voices to a data set or something like that. And another option is to use better synthesis, which has lyrics, for example. One thing is automating choir VSTs. I don't know if you know, but there are many like choir singing plugins that are used by Hollywood people, for example.
See what it sounds like.
They cost thousands of dollars. Maybe I was exaggerating. I don't know if you could hear that well, but it's you can put in lyrics and then it combines samples that were recorded by a very professional choir to synthesize your lyrics. In the beginning, when I was just getting started with my thesis, I thought that could be a good way to generate a data set, but it's very complicated to automate these VSTs, or at least it's very annoying. And another option, of course, is, and I might be a little bit biased because I work at Choral Labs now, but we have very good choir synthesis methods, including some that are in development. So if you use a synthesizer, of course, you also have free, you get for free an aligned score. This is how it could sound.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Susan. Happy birthday to you.
So yeah, I don't think we should give up on synthetic data sets. Just make them better. Other methods is using, another idea is to use unsupervised separation. One paper from Google from like a year or two ago for separate de-reverberating mixtures used unsupervised learning and showed it was pretty effective. In terms of things that I didn't even try to do, I think it's very important to try and integrate instrumental accompaniment separation, because real world choir recordings many times have instrumental accompaniment, and we should definitely integrate that into the pipeline. Also is important to integrate score alignment in some way, or transcription. There are many possible combinations, of course. And I think in terms of input features, if I would do this whole thing again, I would actually not use the raw audio. It led to more headaches than actual gains, in my opinion. Can use spectrograms or whatever, learn filter banks. I don't know, many things to try. That's basically it. I'll be happy for any questions.